Hello, my name is Brian and I'm the chairman of the Mars Rover Society at Binghamton. This year we have collected a group of talented individuals in engineering, biology, and geophysics to help lead our team towards success. By working in a tight schedule under strict administration, we have worked non-stop to achieve our goals under requirements and standards that fit what we personally think is best for the competition.
The mechanical platform is composed of three major subsystems: suspension, frame, and wheels. After thorough research and comparison of alternative designs, we implemented a simple yet robust 6-wheel rocker bogie design to climb obstacles up to 2 times our wheel diameter. We optimized our suspension system using analysis tools to experience minimal deflection and straightforward driving, as well as lateral turning. The Rover's frame was designed to be lightweight, primarily to keep our center of mass low and remain stable at steep inclines. Coming in at only 7.5 kilograms, we were able to utilize heavier and stronger parts for the suspension. Our custom sheet metal design made by Protocase is also sealed off from the environment and provides active cooling to electrical components. We are currently running the Rover with low-cost rubber wheels and custom 3D printed hubs to fit our gearboxes and reduce weight. For competition, we have a custom 3D printed wheel design that will greatly improve our performance in sand and soft soil.
The primary goal of the electrical platform team is the safety and reliability of the subsystems. 2 8,000 mAh lithium polymer batteries were selected in a hot swappable configuration to provide 1.5 hours of power each. We picked 92 watt brushless DC motors with 1 in 20 gearboxes. This allows the Rover to move at nearly 6 miles per hour and climb 45-degree inclines easily. The power distribution for the Rover is divided between the motor system and sensitive systems such as the computer and communications. Control logic in our converters allows easy switching in critical situations. 2 stop switches are wired on the Rover, with the e-stop to power off just the motors. During testing, additional filtering and protection will be implemented to detect stalls.
The navigation team has been working on designing a computer system capable of processing all the sensor data for the science cache task and autonomous navigation. The NVIDIA TX2 will be used to read data from the sensors, which includes LiDAR, GPS, and IMU. We'll be utilizing ROS to interpret the sensor data and implementing it with other subsystems within the Rover. For the autonomous traversal tasks, we'll be implementing visual-based SLAM algorithms. These algorithms will record specific landmarks in the Rover's surroundings and help create a map for navigation purposes. Odometry and GPS will be processed through an extended Kalman filter to localize the Rover within its own map.
Our goal is to design a user interface and a series of network protocols that will allow for remote control of the Rover through a wireless network, as well as design the Rover's autonomous navigation system. After extensive research, we decided to go with UDP protocols, and our results have been promising. We have successfully tested connections between the Rover and the base station that will allow for control and video feeds to be sent between the two systems. While the Rover is in manual mode, an Xbox controller is used to control the movements of the Rover components. When we flip a switch on the base station computer, the Rover will take over an autonomous mode and use data obtained from the Z camera, LiDAR, and several other sensors to determine the best path. While the autonomous system is not fully implemented yet, the software team has completed several critical components already, such as tennis ball detection. We have been working with a quarter-scale test rover to implement, test, and optimize our autonomous components.
Using Ubiquity's AirLink simulation software, we verified that we should be able to transfer 5 megabits per second at up to 1 kilometer, which is enough to successfully communicate with the Rover's main systems. Our field tests have promising results. We have communicated at 300 meters successfully and expect to have it fully functional within a month.
Using Autodesk Fusion, we designed multiple arms and grippers. Each time we reiterated over our most promising features with the goal that it will be capable of lifting 5 kilograms and operate the equipment expected in the equipment servicing task. We tested and altered our designs in CAD until we felt confident enough to design a basic arm for testing. We are currently working towards our final design and expect to be done within the month. We have also taken the same approach to our end effector, with our current design being an Onyx printed gripper.
The sample collected will be tested for temperature and humidity on board the Rover. We will conduct chemical and physical analysis on the sample to test for pH, grain size, and phosphorus content, among other things. These traces in turn hint at the potential presence of living organisms or the suitability for life of the sample.